such a range of leadership positions in our field. She's been president of the AAS. She's led the solar, stellar, and planetary division here at the CFA. She's been assistant director of the CFA. And so we're really grateful for the effort that all of that represents. I think of more relevance to our talk today, Andrea's career has really kind of transformed how we think about using spectroscopy to probe the physics of stars and their atmospheres and the winds that come off of them. And so we're grateful to get to learn more today, and welcome, Andrea. Thanks so much. Oh, and one more announcement. We still have 1 or maybe 2 spots for dinner on Thursday. We're going to eat outdoors, and it's going to be nicer weather, so we're delaying until Thursday.
Okay. Thank you.
Thank you.
Okay, is this on? Can you hear me?
Yeah.
Okay, great. This is historic, you know. This is over for more than 63 years. We've had the colloquium on Thursday afternoon. So you all are participating in history. We actually had moved it. It used to be 4:30 to 5:30, but then that was deemed bad for children's pickup after school. So then we moved it to 4, and now we've jumped it 48 hours, 72 hours on Tuesday. So you're all participating in something historic. And then I'm going to share with you something historic that happened to one of my favorite stars, and that is Betelgeuse. So what I want to do is tell you a little bit about what we know about the supergiant, where it is in its lifespan, what we thought we knew about it until the year 2019, when all sorts of exciting things happened. So let's start. Why do we even care? Now, I think we're going to need there we go. We're trying a new color scheme now, so we'll see how this works. Why do we even care? Betelgeuse is large, and Betelgeuse is close by. And so what this means is we are able to do something with this star that we can only do with the sun, which is a little tiny dwarf star. We can resolve the surface. And then we can learn all sorts of interesting things about the structure of the surface, and in particular how the stars lose mass. Mass loss for stars is exceedingly important, not only for the star itself, because it affects the evolution, the collapse, what form it will take when it collapses, the supernova light curve when it's a supernova, and the ultimate fate of the star. And the mass loss produces the chemical enrichment of the interstellar medium, essentially, of the universe. This is where the heavy elements are made. They're progenitors of white dwarfs and gravitational wave objects. And lately, we've begun to realize that winds of stars may affect the fate of exoplanets as well. So Betelgeuse is giving us a really interesting, unique opportunity to probe many of the things that we never thought we could do before. Let's go way back. Let's go back maybe, 20,000 years ago. And if you go to the southwest of France and look in the Lascaux caves, you'll see these images of animals on the wall. And in fact, the anthropologists and archaeologists have traced out Orion on the left and Taurus the bull marked in these caves that were created, these artifacts in the southwest of France. And even a century ago, Betelgeuse was extremely important and announced in the New York Times. There was Michelson and Pease who put I-beams across the Mount Wilson telescope in order to make an interferometer and measure the diameter of this star. And they actually got a pretty good number. It still stands good today. And the New York Times featured it above the fold. They called it the Colossus of the Skies. So, and then I noticed the other columns, topics in the other columns are very, very similar. There are travel problems, there are transit tie-ups, and other things which do have a certain ringing to what might be happening today. Okay, and then just this spring, the designer Gucci put Orion, the constellation, on a ball gown and featured it in Paris. So there's broad implications and appreciation of Orion. Okay, what is the current state of the star? It's highly evolved. It's a supergiant. It's very cool. It's very luminous. We believe the central hydrogen fuel supply has run out of it, and the core is now contracting, and we're fusing helium into carbon. And as a result, the rest of the star, as you know, has bloated and is cool to about 3,600 degrees. So it's a really nice red, luminous red star, and big and near. It's big. It's really big. Compared to everything else, including our poor little sun, which I think this is a French slide, is marked Soleil in the upper corner above Rigel. It's bigger than anything else that we know of that's a bright star. Okay, if we put it at the center of our solar system, the surface extends out to the orbit of Jupiter. I mean, the radius is 1,000 times the solar radius. And that's just the surface. That's the optical surface that you see. The ultraviolet, which comes from the extended atmosphere, the higher temperature chromospheric atmosphere, goes out even further, Neptune and beyond. It goes 3 to 4 times the extent of the optical surface. And of course, maybe it already went supernova because it takes 700 years for the light to get it here. Now, the size that we'll be talking about, the size of any star really depends on the wavelength, because that's where the radiation at different wavelength bands arises in different levels. So the optical is really the most dense, the closest in, and it gives us a diameter of about 42 milliarc seconds. The submillimeter from ALMA, or the VLA, moves us out a little bit further, but the ultraviolet takes us way out to 125, and we're talking factors in 3 or 4 when we work in the ultraviolet and measure the ultraviolet emissions from the higher temperature atmosphere. Now, we saw this when we did, a number of years ago, the first direct image of Betelgeuse, which was the first image of the surface of a star other than the sun. And this we did with the faint object camera on Hubble. Unfortunately, that's was taken away shortly after launch. And we obtained a UV continuum images where we found a very hot convective spot. We had about 25 pixels, 5 by 5, on the disk of the star and then beyond. And so we found in that a very hot, bright spot on the surface in sort of the southwest of the star. And we followed that for a number of years. And that revealed for the first time that this hot spot was variable. And you can see in this montage of the Hubble images that we took in the upper left corner marked HZ4. That's just a little white dwarf, and that's tiny. And you can see it's not extended at all. And then as we went on for the next 4 years, these are images showing the same exposure time. There was very little change in sensitivity of the faint object camera at that time. But you can see that clearly the star in the ultraviolet continuum presents varying, it's variable. It presents varying fluxes, and that bright spot moves around a little bit, somewhat in concert with the optical variations, but not completely. Subsequently, when infrared interferometry became available, many folks used different interferometers, including IOTA here. Well, I don't think I know. IOTA wasn't here at this time. And the image on the left, which is taken in the infrared, or 1.6 microns, shows 2 bright spots in the star. So in other words, there are these large bright spots which we believe are associated with convective cells. And then there are simulations in the center and on the right where you see a sequence of over 3 years showing the different appearance of the star in the infrared. So clearly it's big, it's bright, it varies, and has large-scale features on the surface of the star. And people are now doing star-in-a-box calculations with 3-dimensional radiative hydrodynamic simulations, and they can reproduce these hot convection cells. My understanding is they tend to be small, They can't get them to be sufficiently large as we observe, but we're making good progress on that. Now, one of the amazing things about Hubble is because of the wonderful, we're above the Earth's atmosphere and the small apertures that are generally available, we can actually scan across the image and then obtain spectra at different parts of the star. I mean, this cannot be done from the ground. It's incredibly powerful. And as you see on the left, there's a cartoon of, this was I think 100 by 100 or 200 by 200 arcsecond aperture that we positioned at all those little white dots and could measure a spectrum. And so at that point, we could look at each of these spectra and deduce that the star was rotating. We could determine the axis of rotation, which we believe one pole coincided with the bright spot that we had seen, and it was sort of to the southwest where there was there have been infrared plumes observed surrounding the star. We also found that it was rotating rather rapidly, and that has been a puzzle. In other words, this is a massive star. It's perhaps 10 to 15 solar masses. And when it becomes a supergiant, if mass conservation, angular momentum is conserved, you might expect that it would slow down. And it's rotating much more quickly than expected from a single star that evolves to become a much larger supergiant star. Okay, the ALMA image confirmed the axis of rotation that we saw. This is wonderful too because ALMA gives us very small 18 milliarcsecond resolution. And they confirmed what we had found earlier in the UV, both the orientation and the rotation of the star. And they also can measure polarization. And this time they thought there was some mass outflow indicated by silicon oxide emission off to the sort of the 10 o'clock, 11 o'clock, which is to the northeast of the star on the sky. So all these things are falling into place. So let's take a look at what Betelgeuse has been doing for the past 150 years, 200 years perhaps. It shows very consistent optical variability. This figure is from the AAVSO, who are wonderful folks making very precise photometric measures. They were a real resource because our telescopes, Magellan is not going to do photometry on Betelgeuse, I can tell you that. But they certainly are able to do this. And over the period of this 100 more years, there are generally two periods that appear. A 400-day pulsation period, you can see that sort of bouncing along in the next to the last panel, which is believed to be the fundamental pulsation mode of the star, driven in part by the kappa mechanism and opacity mechanism that we know in Cepheids. And then there's a longer period of about 5 years, 2,200 days. And it's not clear what that period results from. There have been speculation that somehow it's a long-term convective cycle period, but there's been no real conclusion that what the cause of this long period is at the present time. So everything was fine, and here's another snapshot of the past 7 years from 2013 to 2020 of the magnitude, the optical magnitude. These are photometric measurements from the AAVSO. And you can see everything is looking pretty fine in 2013. We have a nice, roughly 400-day cycle of minima. And everything was fine until, about December of 2019, when, the magnitude started becoming much fainter. In other words, you could see from its 0.5, it started going down, eventually reaching a minimum of about 1.8 magnitudes in February. And of course, when that started, everything went crazy. I mean, the Twittersphere exploded. It was such fun. I remember going on one of the Twitter links, and someone said, "My calculations show it's going to explode tonight. Hashtag hide." No, now hide. I'm not sure what you do under the desk. What do you do? So everyone was clearly very worried because this had not happened in recorded time or in about 200 years. And so what is going on? Well, just to assuage your worries and your fears at the moment, don't hide under the chair. We think it's going to be a while before that happens. I mean, right now we think it's fusing helium to carbon, and what I really love is the timelines that the theorists present. So they're going from step to step, and then finally as we get to oxygen to silicon, that's 1 month, and then suddenly one day everything happens. So it's going to become more unstable, but I don't anticipate that we will have a colloquium about the supernova in the next year or 2 or 10. So we shall see. By the way, that's also interesting in that people have looked at what is the behavior of a star pre-supernova. And people know maybe 3 months, maybe 6 months, maybe a month, what happens. But certainly my understanding is they don't know the day before. What does it really do? Or 2 days before, or 3 days before. Now, Josh Brindley has promised me that he has dash data sitting on the plates that he's going to pull out and find. And it may be that when the Rubin telescope gets going, we might have a better idea of what's happening here. But right now, we don't know. We do know that it is variable, and all the things that are, all the indications are that we can sleep quietly at night and will not see it as a supernova. Okay, well, it was about a year before this when there was a meeting on stellar surface structure in ESO, and a number of us got together and thought, we might really learn something about this star if we get together. I mean, if we really look at it at all these different frequencies and monitor it and see what's happening. So I put together a group that we labeled the Mob for months of Betelgeuse. And there are lots of people from north, south, east, west, all over the world who have lots and lots of instruments. And so in the past 2 or 3 years, we've been able to use a wide variety, ranging from those in the sky, like Hubble or Stereo or Imawari, to radio, to automated telescopes from here to the Canary Islands, to the Australia, Chile, and even a lot of AAVSO amateurs who have contributed to monitoring the star. So what I'd like to do is start in 2019 in January and give you a year in the life of Betelgeuse so we can see exactly what went on, and I'll tell you what we believe has been happening. We started out in January of 2019 with an image that just happened to be scheduled on the VLT with Sphere. And this is an image near the H-alpha continuum. And you see in the left picture that it looks like a fine star. Maybe there's a bright spot on it, and maybe it's a little bit dim towards the edges, a little bit of limb darkening. But it looks perfectly fine and a happy little supergiant. But at the same time, Katerina Kravchenko at MPI in Garching was working with optical spectra. Now, these are spectra that are of the whole star, and they came from Hermes on La Palma. And what she does is she uses a technique called tomography, where she looks at the optical spectra, and you see a section of it here, and she notes that some lines are formed deep down. When you look at the formation process of these lines, some are formed deep in the atmosphere, others are formed farther out in the atmosphere. So you can make masks and actually track the dynamics of the atmosphere in the supergiant, even though it's from integrated spectra. And what she found was very surprising. From January to March, shocks were developing underneath the photosphere, and the surface was beginning to expand. But meanwhile, the light variation so far was fine, okay? Then we come to a time, of course, when we can no longer see Betelgeuse, and we couldn't see it in 2019 during the summer because it becomes too close to the sun. And so when we finally looked at it with trace, well, we were taking spectra all the way through. This is a calcium region of the calcium spectrum. And what's really important here are these emission lines in the middle, which I mark V and R for the violet side, and the red side of the calcium-2 transition. Because the height of those peaks tells us about the dynamics in the atmosphere. And what we found was that from January to March of 2019, everything was moving out in the atmosphere. This is in the low chromosphere. And then in September, it was back to normal again, back to its normal asymmetry where V, the blue side is higher than, is stronger than the red side. So from 2018, in September, things were fine. And then when we looked at the calcium line, we could see that there were indications of outflow in the low chromosphere, January to March, which had stopped by the time September rolled around. Now, at the same time, there's an amazing telescope on TA Day in Tenerife, run by the Leibniz Institute in Potsdam. And they have an automated shell spectrograph, and they measure the radial velocity of this star every day when it's accessible, including COVID, because it's totally automatic and remotely controlled. So they didn't even close down, they just kept on going. And what you see here is a plot of, about 10 years of their radial velocity measures. And you can see there's a perfectly fine oscillation up and down with the 400-day period. This is the photosphere now, moving with this 400-day period. And then in January of March 2019, the surface outflow started. Now, when the scale is such that as it moves towards the bottom, it's moving out towards you. So you can see that the surface outflow started January to March 2019, and then there was a long extended time, much longer than usual, of a maximum outflow from the photosphere, September, November of 2019. Now, at the same time, we were fortunate enough to have Hubble observations, and this time we were using a rectangular aperture, one of the smallest ones available on STIS, which is about 25 by 100 milliarc seconds. And again, we could step it across the disk of the star and obtain a spectrum at every single position. And we were able to look at the magnesium-2 lines. These are very strong chromospheric lines that are formed obviously above the surface of the star, and they also can give us diagnostics of the dynamics of the atmosphere. And first of all, we found, and I'm showing this in the plot on the left, where the southeast part of the star is on the left and the northwest is on the right, and that corresponds roughly from 7 p.m. to 1 p.m., like a clock. I mean, we take the Hubble positions as they give them to us, and they tend to follow that arrow, that direction in terms of the axis of the spectrograph. And what we found was that in September, October, and November, you see these red points. It shows the flux in the magnesium-2 lines. It was enormously enhanced over what it had been in March, and also enormously enhanced over what happened subsequently in February and April of 2020, just when the optical part of the optical magnitude was getting much dimmer. And we think that what was happening is that there's a strong magnesium-2 flux, a cloud, that was coming out of roughly the southern hemisphere of the star at that time. Now, we can also do other things with the ultraviolet spectrum. It's extremely powerful. There are certain diagnostics there produced by different atoms, and this one happens to be carbon-2, where by looking at the ratio of different lines, this can indicate what the electron density is in the atmosphere, because of the way the collisions in the atmosphere affect the populations of the levels. So we could look at those lines. We've marked the lines here, 23, 25, 23, 28, and look at the ratio as a function of time. And that's what I'm showing in the right figure. The red and blue points indicate, the red point indicates the southern offset, and the blue points indicate the center. And you can see as we start out in the early 2019, the ratio indicates there's a lower density. And as we move through September, October, November, just when we saw this cloud coming out of the south, the density diagnostics indicate that this is a higher density cloud moving out. And you say, is it moving out? Well, of course it is. It turns out that you can look at the profile. Again, very similar to the calcium lines, only in this case, models on the left show us what the response of a magnesium-2 feature should be when there's a traveling pulse. You send a shock through a star. This is being done for a stellar atmosphere. And when you send the shock through, the change in the profiles, the strength of the profiles is very obvious. That the blue line, which indicates material is coming up suddenly, becomes stronger. And we see that exact behavior in the fall of 2019. So we see that, okay, the star is becoming, is being subjected to outward motion in the chromosphere of dense material during this particular period of time. And remember, Betelgeuse is big. So if you have something starting at the photosphere, by the time it gets out to 1,000 or 2,000 stellar radii at 10 kilometers a second, this is going to be 4 to 6 months. So it takes a long time to get out there, and we can watch it moving out sequentially. Okay, so what we think happened is that at this particular time, causing the bright outward motion ejection of this material was a confluence when the radial velocity of the photosphere was moving out for a long time. And most likely there was a bright convective cell, which is indicated by the shocks that were identified in the photospheric, in the optical spectrum. And we think that this is what combined to eject this material, which takes about 6 months to move out. Now, in December, we again went back and took another image, this time with stereo and Zimpal. And you can see on the left is the image of the star in January, and here, look at the right is the image of the star in December. And clearly, something has happened, that the whole southern hemisphere is very much weaker, as if there's a cloud or something, maybe it's getting fainter. Something has happened to the southern hemisphere of the star. There were no transits of other stars, no transits of disks that it could have caused this. And the modeling that the folks carried out in Europe who obtained this image, suggesting that dust may be the culprit that produced this particular image. And that would make sense. You have this hot material moving out. It goes to a point where it's cooler, and then you can become molecular, and then you can start nucleating and producing dust. And it's all in a period of 6 to 10 to 12 months. Okay, now we were following it also with a trace spectra from Mount Hopkins, and we found 2 things. In the left, you see a typical combination of the spectrum, and we see that in October, well, I guess we started in August, or April, excuse me. In April of 2019, it had deep, deep lines, which then became weaker in October. And then by February, that's indicated by the red curve, it's extremely weak. And this is very typical of a cooling atmosphere. If you look at other stars that have different effective temperatures, they all have much, much weaker lines. And there's another diagnostic we can use, which is a ratio of the vanadium to the iron 1 lines, which I've marked on the left. And when we look at that particular ratio, and I marked it on the right in the red with the red dots, you can see that that's also following the light curve of the star, indicating that indeed the temperature appears to be getting lower. So this is when the chromosphere has survived, but the surface of the star is much cooler, by anywhere from 300 to 600 degrees. Okay, now there are many diagnostics. We had Betelgeuse attracts lots of attention, and people use, as I showed earlier, many instruments and techniques and things to understand what is happening. Normally, the temperature is about 36, 50 degrees. The TIO bands and the optical and the near-infrared suggested a cooler temperature during this time, December through February. The sub-millimeter measurements, VLA, also suggested a cooler temperature. Infrared spectra suggested a cooler temperature. And then some measurements were made at 10 microns by the Himawari satellite, which suggests that there's increased oxygen-rich dust that was measured at 10 microns in this December-February time period. Matisse finds a localized cool spot and some indications that there's increased photospheric turbulence during this time. Okay, what happened? Here's what we think happened. That we first started out in January through March with the surface outflow seen from the optical spectra. In the fall, which is okay, 6 to 8 months later, we measured this chromospheric outflow from the ultraviolet spectra. And in January and February of 2020, we see this surface that appears to be cooler, and there appear to be signatures of dust, both in the optical image and also from spectra as well. And we believe that what's happened during this time was what we call a surface mass ejection. That's propelled by the shock, the pulsations, the period of the pulsation, and perhaps a large convective cell that occurred at the same time. When I say large, it really is large. I mean, this is on the order of a quarter, at least, of the surface of the star. Maybe there's a magnetic field. There's no indication. Well, there's an indication of an overall weak variable magnetic field, 1 kilogauss, that's it. But no other indications of magnetic field, but maybe there's a magnetic field involved. And the result is a cooler, less dense photosphere. In other words, if a large amount of the photosphere was ejected, what's going to happen to the rest of the photosphere? Then the plasma around it is going to expand, it's going to be cooler, and it's going to be less dense. This is the first time anything like this has been seen directly. And when we look at the amount of mass loss that's involved, it could be quite substantial. There's some uncertainty because there's an uncertainty in the distance of the star, and an uncertainty in calculating this, assuming a dust model. But it ranges from 5 to about 100% of the normal mass loss. The star normally loses mass on the order of 10 to the minus 6, 10 to the minus 7 solar masses per year. And this appears to be potentially comparable. Okay, many of you know about SMEs. They happen in the sun. I mean, CMEs happen in the sun, right? These coronal mass ejections. And I have a nice AIA image of the helium line showing a coronal mass ejection. There's a substantial differences. The time scale that we see in the supergiant is months versus minutes that a CME takes place. The size that's involved is quite substantial. It can be a quarter of the solar radius, of the stellar radius, versus, as you see here, something that follows a flare on the surface of the sun. Actually, when you try to do a mass estimate, it looks like from Betelgeuse we're losing several lunar masses, several times the mass of the moon went out with this particular event. And the mass loss in Betelgeuse as compared to a CME is billions, much more than a CME. And the frequency is also obviously quite different. Years versus much more frequently with the sun. Okay, and we wanted to follow it. I mean, what is happening? This occurred, of course, at a very critical time because Betelgeuse starts becoming inaccessible from the ground in about April. And it doesn't recover again until September, late September. But then we realized that there's a satellite called Stereo, which is a solar satellite. And it's very interesting because the orbit of this satellite is in the Earth's orbit. It follows, at this time, it followed the Earth by 3 or 4 months. So when we could not see Betelgeuse because it was July, this satellite thought, oh my goodness, it's fine, it's March, I mean, I can see it. And they were really wonderful, and they agreed to lose contact with the Earth, torque the, reorient the satellite, and take images, because they have a big CCD with a large field of view, and they have photometric stability with their CCD, and we could do photometry using other nearby stars. And that was when we found these red points. Here it is, May, June, July, and what I show you on the right is a picture of the optical, the V magnitude variations, and then that thin line, broken line, that's the 400-day pulsation, okay? That's the 400-day period that we expect to see, right? Well, May, June, and July came on, and uh-oh, it wasn't getting brighter again. It was getting much dimmer, according to stereo. And at the same time, unbeknownst to us, and you should think about this is really thinking outside the box, some very clever Japanese grad students realized that they have a satellite called Himawari. And it's a geostationary meteorological satellite. And it takes pictures in 16 different filters, ranging from the optical all the way through the near infrared. And they take pictures, every 20 minutes, all the day, all the time, of the Earth. And you see the picture on the left. Well, those clever people realized that off the corner of the Earth, between plus or minus 7 degrees from the ecliptic, is lurking Betelgeuse. What else? So you could see they found it. And then there it is in the bottom. And they could do photometry from it. Very good photometry. So it's not bothered by getting too close to the sun or not too close to the sun. It works fine. As a matter of fact, NOAA, we have a satellite like this. It's called GOES, G-O-E-S. And we've been talking with those folks, and they have millions and billions of images that we could use. But NOAA uses a really weird data format that we've been fighting with. So it's unique to NOAA, but we'll get there. But you should really think about this. I mean, using other capabilities is just a real innovation in astronomy. I think they claim the first astronomy measurements from a meteorological satellite. Okay, so what has been happening? Let's keep on going now. We followed it in the top. You could see right after January, February, March, it missed its pulsation. We still indicate by the sine curve in the top panel that there is a 400-day pulsation. That's what it should be. And you can see that has not happened. Not only has it not happened, it's missed, and the pulsations are smaller, are getting shorter in time. And in the bottom panel, you also see the radial velocity. That, again, is showing a smaller amplitude than what has happened before. It's almost like when you take out, imagine a big hunk of the photosphere, and then the star tries to recreate and come back again. I think the people at Space Telescope press release said, it's just like a washing machine that's in imbalance, and it's trying to come back. I don't know, maybe I shouldn't have used that or let them use that, but you could immediately identify with that for real life. But you can see that the excursions are not back to its 400-day pattern. I have a number of observations in the top figure, and one of the other very clever ones is a retired professor of physics in Germany who's the AAVSO member, and has realized that if he takes hundreds and thousands of pictures in the daytime of Betelgeuse, he can derive good photometry by that and comparison stars. And so when it's not cloudy in Bavaria, we get more data, and it's wonderful. And he has filled in many of the open triangles there, open diamonds, I guess, with these photometric measures. And even now, I've filled it out to, I think, 2 days ago. Is it coming back? I really don't know. It seems like it's turning over. It's got a little bit fainter in the past week. And we're hoping that it would recover it's 400 days, but it doesn't seem to be, or it's thinking about it. So stay tuned. You might ask, is this unique? Has anyone ever seen this before? And actually, there are some indications of similar events, similar surface mass ejections. In particular, one of the most famous is perhaps the VW Canis Majoris, which is a supergiant. It's slightly hotter than Betelgeuse. And Humphreys and collaborators have done a lot of great deal of study, observations and study with the Hubble Space Telescope, looking at the emission knots, and they're marked here. She's marked them various things around the star. The star is completely obscured, so you cannot, no hope of looking at the surface or getting in closer. But you can look at these knots. And with Hubble, they've been able to measure the velocities and the proper motion of the knots. And then they run them back to when they might have left the star. And they contend that when they were at the star, that the star may have been behaving in unusual fashion. Not clear what that is. Maybe a little bit of optical variability. And since then, I've gotten lots of emails from people who say, oh, my favorite star did something like that. So, I mean, L2 Puppis has shown a lot of optical fading, but never the same kind of ringing that we've observed with Hubble afterwards, with Betelgeuse. 89 Her also it's a yellow supergiant, and it has a optical pulsation that's shorter, and at one point it stopped, and then it just bounced around a little bit, and then resumed. But none of these objects, and then most recently, an alumnus from here, Jay Strader, was in part of a paper with a dimming of a supergiant. They were looking for failed supernovae, and they contend that in M51 there was a supergiant that went down by 2 magnitudes. But none of these observations are as continuous and as wide-ranging as what we have for Hubble, for Betelgeuse, so that we have much more indications of what was going on from the photosphere on out. Okay, so what's next? Well, in 2023, we calculate that this material is moving out, and if it's moving out at a reasonable 10 kilometer per second velocity and out in the plane of the sky, it should be observable with ALMA, which has a nice 18 milliarc second beam width, and we can observe dust with that. So we're hoping to go chase it down and see if we can find it. Another, perhaps, well, I don't know if it's a cause or not, but there's been some chatter that maybe the 2,000-day period and the 400-day period, when they have a certain phasing, a certain minimum of the 2,000-day period, followed 300 days later by the 400-day period, that's when things happen. Not clear, but it's going to happen again in 2025, 2026. So we should keep an eye open at that particular time. We have the GOES satellite data that is ongoing and coming. We have more HST measures continuing. We also have started some hydrodynamic simulations and some radiative transfer calculations, which have to be, very non-LTE and spherical and everything in order to really interpret this for the first time. And then I just heard that Betelgeuse is going to be occulted by an asteroid in December 2023. And so we should all head to Greece and see it. And that's apparently where it's visible. And there's a group called Asteroid Transit Volunteers, and they've already made videos of Betelgeuse getting fainter and just disappearing and then coming back again. And so it's going to transit. It's going to take 7 seconds. So don't blink, just watch and see what's happening. So I want to thank you. Let's keep watching. Thank you. And I'm happy to take questions or other questions.
Yeah, so go ahead and ask questions. We may chime in with some questions online. Folks who are online can type them
Oh, you've got online too, good. Oh, gosh,
There's
okay.
70 people watching online.
Oh, my goodness, okay. Okay, Peppy? Yeah,
Has Chandra looked at Betelgeuse?
I'm sorry, I can't hear.
Has Chandra looked at Betelgeuse?
Oh, yes, I should have mentioned that. When this first started, and it started getting dim, it was Vinay Kaushik who thought, oh, maybe there's a shock and maybe we'll see X-rays. No X-rays. No X-rays. Of course, remember, it's got an enormous atmosphere. So it's not clear X-rays would make it out unless it was somehow a convincing, I don't know, a hole in the atmosphere or something. I'm not sure. Yeah. Yes, question, Mercedes.
Yeah, so, one thing that caught my attention was when you said that it is rotating too fast, and I don't know why.
This is what?
That it is rotating too fast.
Yeah, oh, it is, yes.
So have people looked into scenarios where the star has engulfed, like a companion
Oh.
or something like that?
I should mention, when we found this, Han and I found that it was rotating too fast, and this was right in 1996, right after 51 Peg was announced. And we said, oh, maybe it engulfed a planet. Well, it turns out it had to engulf a lot of planets. Lately, people have been doing syntheses. It turns out that a fair proportion, I think it's something like 30% of supergiants can have, on the main sequence, can have binaries, can have companions, okay? And they've been doing simulations showing what would happen if it engulfed, because as it expands and it would engulf a companion. And that would give it this fast rotation. I mean, it's like 30 years, I think, or something like that at this point is the period. And that is plausible. And the question is, are there other signatures of an engulfment? Okay. It is also unusual in that it's got a very high space velocity. And when you trace it back, it doesn't go back to any star-forming region. And so then what happened? And so there are other people who suggested that maybe it was a companion to a star that went supernova and then was ejected as a result of the supernova event. So it's still open, but it's rotating quickly. And that's also interesting because there's a wonderful paper by Neuhauser that just came out where they went back to Aristotle and Chinese observers and things who looked at the brightness of these stars, these very bright stars like Antares and Betelgeuse, relative to the planets. And they contend that there's evidence that Betelgeuse was much bluer, maybe 1,000 years ago, and that only recently it went quickly across the Hertzsprung gap, just got there now. And it may be that it's very early in its in its ascent of the supergiant branch. So there's a lot there's a lot of information out there about this star, and it's not settled yet. I think it's fair to say. And when they do their calculations, they say that introduces another problem. Neuhauser and all use mist models, which are great models. But they didn't use them with a rapidly rotating envelope or core. So are those models then valid? And can you say that it really was blue 1,000 years ago? I don't know. But yeah, there's lots to think about. Hi, yes.
Yes. So I'm trying the interpretation of this. Should I be thinking of this as like a CME, which is essentially a launching of photospheric material out into space? Or is this something where it's like the hot material down in the interior is welling up and blowing out the atmosphere?
It's the hot material down below. The CMEs generally happen in the corona, and they're very fast. And they find that after the material is ejected, the density is lower in the corona. And when they do an emission measure, this is analyzed by looking at a lot of high temperature species, iron 12, 13, 14, high temperature species. They find that the emission measure decreases so that the temperature went down as well. So that's from the corona. In other words, to my knowledge and consulting with the solar experts, it might affect the high chromosphere, but never from the photosphere. I mean, there are things like spicules from the photosphere, but those are not massive ejections like the coronal mass ejection. So we're saying this is coming from the surface. It's a lot of material. And it's coming, it's a totally new thing, a totally new phenomenon that may affect the substantial mass loss of the star. So it's sort of fun to see if we can
So do you,
understand it some more.
so
Yeah.
do you see internal products like carbon and things like that that have been generated in the interior that are now being able to be seen?
Yeah, would the abundance change?
Yeah.
Now that's interesting. Okay, we haven't looked. I'll have to get work with some abundance people, see if that something like that might happen. Yeah. Now, we're trying to do the tomography now with the ultraviolet lines as well, and so Katerina, we've got some masks for the ultraviolet lines so that we can try to follow it through. And also with spatial resolution. In other words, we can do it in the center, or at the side, or at the limb, or something like that. That's going to be good. Yeah. Yes, there's a question way back.
Yeah, so speaking of the 5 years period that you earlier mentioned.
I'm having a hard time here. You're going to have to
I'm
speak
sorry.
up. Sorry, you're under that.
Speaking of the 5-year periodicity that you mentioned earlier, is this any chance that the surface mass ejection also happened, that like the very actually deep in the velocities and so on?
Well,
You haven't shown it.
yeah, I did. People have speculated that the 2,000 day period reaches a minimum. In other words, in the optical light, about 300 days before the 400-day period reaches its minimum, and that's when things, quote, might happen. And now, actually, it was Leo Goldberg, who was my thesis advisor, who promoted that, but then he didn't have the data to prove it. I mean, when you look at the data that was available at that time, and he said something was going to happen in 1987, and it never happened. Okay, but never give up hope. Maybe there'll be something there that's interesting. And so that's going to happen again in 2025, 2026. So we'll see.
Quick follow-up, or
What?
is there any chance that you can also observe radio emission out of this or
I'm
not?
having a hard time.
Is there any chance you would observe radio emission?
We have been looking at it with the VLA and with ALMA to get effective temperatures, and that's a challenge. We had VLA time actually in August of 2019, and the temperature was much cooler than expected. But there's a question about where the millimeter and centimeter radiation originates, because we know that the atmosphere is very inhomogeneous. I mean, there's cool stuff, there's molecules, there's hot material, and we're not sure how the plasma producing the radio emission reacted to the shock that went through. And there are some calculations, I believe Mark Reed did some of these showing the effect of a shock on radio emission, and contends that you could get different temperatures at different frequencies at different times. So we're trying to pull all that together. But you can get radio. And ALMA is wonderful, because ALMA, you could see the disks around it. You could see molecular emission. You can get velocities. It's really good. Yeah. Okay. You sorry.
So about the two periods, Andrea, in kind of semi-regular variables where you see this behavior, there is an indicator which is in the O minus C diagrams, observed minus calculated.
Right.
So you see a phase drift between the two.
Oh. Okay.
And it looks like stepwise. It has a stepwise
Oh,
form.
cool.
Now, here the period is long, so you have to look in the historic AVSO data. But have people looked at the O minus C diagrams?
No.
And would you?
No, that's a traditional, old, from your PhD thesis, okay. That's it, I'll talk to you about that, yeah, no. We all do, everyone does analysis, Lone Scargo kinds of things, and Fourier transform, all these things. But not a good old O minus C diagram.
Phase drift.
Yeah. Okay. I don't know if all the observations going back are kind of spotty, but we could try that, especially for the long period is going to be tough. Yeah. Okay, that's a good idea.
Can I
Yeah.
share an online question?
Oh, sure.
And would you mind repeating it also for the
Okay.
people online?
Okay.
So Rosenda Stefano was wondering if there's a preferred direction for the outbursts in general, and including that one beforehand.
Yeah, is there a preferred direction for the outbursts? We have two examples, let's see, well, three examples. Two examples of infrared plumes or ALMA detection of SIO, which seem to come from the axis, from the poles, either the South Pole or the North Pole. This one appears to be from the south. We can't say that it's really from the South Pole yet. We can't say that. And Roberta Humphreys has taken a look at the dust pieces around Betelgeuse, and there does not seem to be a preferred direction. But she does not have much luck driving them back to the surface of the star. Nothing strange happened at those times that produced that. But that's why I would love to look with ALMA, because I'd love to see, can we get it from some other place? I mean, people used to think that we have rapidly rotating, or we have rotating stars, if the distance to the poles is shorter because the star is flattened, and you know, trouble will break out in the poles, and that's how it should be. But if it's not coming from the poles, and like VW Canis Majoris is coming from all over, as far as we can tell. I mean, there doesn't seem to be a preferred direction in the work that she's done with that.
Super interesting.
Yeah.
And then Ed DeLuca is asking, is there, in the radiation hydrodynamic simulations, does the convection impact the rotation rate? And also, can you do astroseismology with this pulsational light curve, and does that give you any insight about the atmosphere?
Well, a lot of that's above my pay grade, let me tell you, but I think that you want me to repeat the question. Can I learn anything from radiative hydrodynamics about...
Yeah, or astroseismology.
Or astroseismology. People have started to do that. Meredith Joyce is someone who has started doing that. And she's coming here, I think, for an ITC seminar
later this month.
Later this month. But certainly not to the level that's been done with Kepler or TESS or anything like that. The 400-day pulsation, people who model it say that that's what you expect. That when you look at semi-regular variables, a star at this color and this luminosity should have a 400-day period, and that seems to be, underscored by lots and lots of different stars. But in terms of doing the radio, well, that's what you're going to start doing, right? I mean, we're going to have all the answers to that.
Right.
Okay.
I think we have time for maybe one more question.
Oh, hi. Oh,
Hi.
yeah.
Yeah, it's all pretty spectacular stuff. Can you say more about the mass estimate of the SME? How does one actually get that 10 to the 9 number?
Okay, that comes from the dust modeling right now. We're trying to model it with the magnesium lines using radiative trend. We're gearing up with some actually solar codes from solar physics, the Rybicki-Hummer codes that Han has made available. But that right now that comes from the dust, the modeling of the dust, and that's has a lot of free parameters. I mean, it really does in terms of the makeup of the dust, the distribution of the dust, the gas to dust ratio. All of these things enter into it. And then on top of that, we have the distance to the star, which is there's some controversy about the distance. So that's why when the estimate came up about how much mass was lost in this, I think it varies from 5% of the total to 130% of the total. So of total solar mass loss per year. So stay tuned. That's all I can say. Hopefully we'll get a better estimate.
Listen, thank you
Okay.
one more time.
Thank you.